This video was brought to you by GeneralPack.com, making power systems intuitive, open, and free to everyone, everywhere. Consider subscribing and supporting through patreon.com/generalpack. This is the mechanism for you to support us financially so we can continue making high-quality power system video tutorials. Our corporate sponsor for this topic is AllumiaX.com from Seattle, Washington. Contact them for industrial and commercial power system studies. Introduction to Fault Analysis Part 3d-2, Line to Ground Faults. In this video, we will consider the sequence voltage components and phase voltage quantities for a two-line to ground fault on the 13.8 kV side of the delta Y transformer. This is a continuation of Part 3d-1. Now, for this, we have to look back at our faulted sequence network and having a closer look at the network diagrams and paying close attention to where the positive, negative, and zero sequence voltage quantities are actually measured or calculated, which is the 13.8 kV side of the transformer. We can clearly see that all three sequence networks are connected to the same node. And therefore, by way of Thevenin's theorem and basic circuit analysis, we know that all sequence voltages will be exactly the same. Now let's calculate the positive sequence voltage and then go from there. So the positive sequence voltage is calculated by simply taking the source voltage, which is at 1 per unit angle 0 degrees, minus the voltage drop of the sum of the impedances in the positive sequence network. And so that is, the sum of the impedances is J.15, and the current flowing through the positive sequence network is negative J 4.7619 per unit. And what we get is 0.285 per unit at the angle of 0 degrees. Now we know that all of the sequence component voltages will equal 0.285 per unit. And we can multiply that by the base value of 13.8 kV divided by the square root of 3 to get the voltage quantity, which we get as 2.27 kV at the angle of 0 degrees. Now, as a full and final step, the sequence voltage quantities need to be transformed to a phase voltage quantities, and we could do that by plugging them into our legacy equation, which we show below. Now, since the positive, negative, and zero sequence voltages are all equal, we know that phase A voltage will equal 3 times the positive sequence voltage, and that is equal to 3 times 2.27 kV at the angle of 0 degrees, which gives us 6.829 kV or 6.8 kV at the angle of 0 degrees. And when we calculate the phase B and phase C voltage quantities, it happens to be reduced to 0. And this makes total sense, especially by looking at the earlier diagram that we drew for a double line to ground fault on the 13.8 kV system. We know that phase B and phase C were the faulted phases, and we also know that the voltage at the point of the fault will be driven to 0. And so it makes total sense that the voltage at the point of the fault is simply equal to 0. So there you have it. Now we have calculated both the fault current values as well as the voltage values for a two line to ground fault, and in the previous videos we've calculated the line to ground faults, the line to line faults, the three phase faults, and so forth. Now in the next video, in part 4 of our series, we will see how we can reflect fault calculations over the high voltage side, given that the fault was at the low voltage side of the transformer. And this is going to be very, very unique, and a lot of the times it's quite confusing for this because there are special things that we need to consider in order to analyze the fault values on the high voltage side from a sequence components point of view. So this is going to be covered in part 4. Now we hope that you find this video tutorial valuable and useful as a professional or student, and we hope that you support us by becoming our patron and subscribing through patreon.com/generalpack. Your generous subscription will help us continue make high quality power system video tutorials. Thank you.